Hello everyone, good morning, afternoon, evening, whatever time it is you're watching this. In today's video, we're going to look at one of my favorite applications of derivatives, and it's called optimization. We're going to take some quantities and we're going to try and figure out the most efficient way to do something. So let's just jump right into it. Example 1, let's see, rectangular farmland, 3 sides, single strand electric fence, with a certain amount of wire at your disposal. What is the largest area you can enclose? What are the dimensions? Okay, so like I told you, we're going to try and do something in the most efficient way possible. So this is what we're trying to optimize. What is the largest area you can enclose? We want to have the most area, but look at this guy back here. I'm going to switch colors. Oh, I'll highlight it. With 1,000 meters of wire. So every optimization problem is going to come with what's called a constraint, and that's what I just highlighted in yellow. Constraint. And you need a constraint to help you reduce how many variables are in the problem. Let's make a picture, and I'll kind of show you what I mean. So it's a rectangular plot of farmland, 3 sides with a fence, and on one side by a river. So here's our river, river. And then here is our farmland. We'll just call it area, because I'm super creative. Okay, then our constraint is that the perimeter of that fence is 1,000 meters. So let's just say hypothetically, well, in math we like to use y for things that are vertical and then x for things that are horizontal. So our perimeter, actually I'm going to put this over here in the regular part of the problem. Our perimeter is given to be 1,000 meters, because we have 1,000 at our disposal, and we know that it's going to take 2 lengths of y and 1 length of x. That's what it's going to be made up of. Our job is to maximize the area. And why don't we come up with a function for area? Here the area would be the product of whatever you named those 2 variables for your length and width. So here's the deal. Like I said, the constraint usually helps you reduce the number of variables. How's it going to do that? Well, let's talk about our general strategy for the problem. How do we find a function's maximum or minimum value? If we were looking for a maximum, like we're kind of looking for area here, well, we need to figure out where the tangent line is horizontal. Where is that going to happen? Well, we take the derivative, we set it equal to 0, we solve. We've done that in the previous sections. That's what we're going to do here with optimization. The only difference is you're given context, you have to set up the problem yourself instead of being given an equation and told to find the max or min. So if I have my area function of x and y, how am I supposed to derive that and set it equal to 0 when I have 2 variables? You might say, okay, well, we could implicitly derive it. Could we, though? Is that really going to help us? We're still going to end up with so many variables. For optimization problems, our goal is always to get down to 1 variable. Goal, get to 1 variable. And that's where the constraint is going to come in handy. So we have our area, again, is a of x, and our perimeter constraint is 1,000 equals 2y plus x, or x plus 2y. So let's make a substitution somehow. That's where your constraint comes in handy. So how about instead of 1,000 equals 2y plus x, how about let's just slide over that 2y. Let's do 1,000 minus 2i equals x. Because now I can make a quick substitution into my area function. So now my area is going to be, I'm going to substitute in here for x, 1,000 minus 2y times y. And it doesn't matter that I'm using y or x. You could have solved this the other way. It doesn't matter. The important thing is that we've gotten down to 1 variable, and we can kind of consider that variable to be an an independent variable. So really what we have here is area as a function of y is 1,000 minus 2y in the quantity times y. And you can multiply this together. In fact, let's go ahead and multiply this together, because the next thing we're going to do is take a derivative. Do you want a product rule, or do you want to just use the power rule? I don't know about you, but I just want to use the power rule because I'm lazy. I mean efficient. I'm efficient. Okay, so up next, like I said, we're going to take a derivative. Why are we taking a derivative again? It's because we're looking for a maximum or a minimum. Here, we're looking for the largest amount of area. So we want to maximize this area function. We find maxes and mins by taking a derivative. You can either notate it with the a prime, because that's true, or officially what I'm doing here is I am taking the derivative with respect to whatever variable you had left. In this case, it'd be y. So the derivative with respect to y of both sides. And now let's go ahead and derive that. So I will notate that as a prime of y. And then over here, derivative of 1,000y would be 1,000. And then minus the 2 comes down, so 4y. Okay, that's great. What we have here is a measure of how it changes, how area changes based on this length, which I guess is actually a height, but we'll call it length. And again, we wanted to maximize the area. We want to find where the area is a maximum. Well, how do we find maxes or mins on a function? We set them equal to 0, because that's where the function would have a horizontal tangent line. Whoops, that should just be one line. 1,000 minus 4y equals 0. And I'll leave a note here to find max min. Now let's solve for y. So let's add the 4y over. Divide by 4, you get y equals 250. Okay, so when y is 250, when this length here, when these two lengths are 250, and then that would make this other length 500, which we'll verify that at the end, that's going to maximize how much area is in here. Anything else is not as efficient. Let's see. We got to prove it real quick. I guess I didn't prove it. I just said, oh, it must be a max. Hey, you know, it could be a minimum. So let's verify it real quick. Let's think. What's your favorite way to check that something's a max or a min? You can either use the first derivative test, or you can use the second derivative test. I personally think that second derivative test is going to be a lot less work here. So let's just come back. Here's our first derivative. Let's just stick this off to the side here. The second derivative there is just going to be -4. So this function is always concave down. So if I've got a critical point someplace where I know the tangent line is horizontal, here's the horizontal tangent line, here's the horizontal tangent line, and then the function has to be concave down, okay, I know it's this one. I know it's got to be a max and not a min. Okay, before you finish the problem, I want you to ask yourself, did you find everything? This is a common mistake people make on these problems. Did you find everything? Let's go back to the question. The question is, what is the largest area? And what are its dimensions? I kind of covered up the and with this circling here. What is the largest area and what are the dimensions? Well, so far, I found the y. I did not find the x. I did not find the area. Well, you could use your constraint. That's probably the easiest way to find the other variable, since we said 1,000 minus 2y equals x. Well, okay, 1,000 minus 2 times our answer equals x. So our x has to be 500. Okay, there's something else we needed. And then put them together to make the area. 250 times 500, push the buttons, 125,000. And I think it was meters. Was it meters? Yes, meters. So let's answer in context to meters squared. Now we've answered everything. Now we finished. So isn't that kind of cool how we could use a little calculus to figure out a logic puzzle like that? Maybe it wasn't a logic puzzle, a math problem like that. When you're ready, let's turn the page. All right, we got another problem here. It's slightly different, but it's the same idea. All the problems, well, it's the last problem for today's video because these take a while. The problem in tomorrow's video are the same idea, optimization. You want to either maximize or minimize some quantity, but you're going to have to come up with the function to do it along the way. So let's see. A rectangle has its base on the x-axis, and whoop, my computer's tweaking out. Has its base on the x-axis and its upper two vertices on a parabola. What is the largest area this rectangle can have, and what are its dimensions? Well, let's make a picture. I made a picture for fun on the last one. You could probably get away without making a picture on this one, but I would definitely need to make a picture for this one. So we're looking at a graph. I know from pre-calc, my knowledge of the 12 basic functions, which I tried to smack over your head, that this would be a parabola that opens down and starts up 16 units high. So we don't necessarily need to be to scale, but if nothing else, I need a little something like this. What else do we know? We are actually looking for a rectangle inside here. Its upper, oh, it has a base on the x-axis. Okay, so part of the rectangle is going to be down here. And its upper two vertices exist somewhere on the parabola. So some people get hung up on this. They're like, I don't know where to put them. That's okay. We're going to figure out where to put them. We're just going to say our figure is not to scale. So somewhere on the parabola, the corners of our rectangle touch the parabola. And where it's actually going to happen, that's what we're going to figure out. Okay, our question is, what is the largest area the rectangle can have, and what are its dimensions? So kind of the same thing as the last one. All right, what on earth are we going to do here? Well, let's take a look back at what we were trying to do. We need to identify a constraint. We need to identify what we're trying to optimize. So we're trying to optimize area, so we should probably come up with some way of representing the area. And then we've got to find a constraint somewhere too. So let's see, I'm going to change my color here real quick. Well, if we were going to find the area of this rectangle, we would have area is base times height, right? So we need to come up with something that represents the base, something that represents the height. You can use h for the height. You can use y. You can use your favorite letter. I don't care. For simplicity's sake, why don't we say the height here, we're going to go ahead and call that y. And then we need something to represent the base. And you can either say, well, all of this length is the base. But thinking about what we have here, something with x's and y's might be kind of helpful. How about this? Let's split it up. If we want to stick with x's and y's, because then it might help us use the other equation, from one side to the other would be length positive x, right? Because it's from the y-axis to wherever you're stopping the thing. And then, well, that's not the whole rectangle, though, so we'd have to come back this way. Going back this way would be, I guess, negative x, but it would have length, that thing that's always positive, length of a positive x. So really, I think my area, my base times my height, would really be 2 length x times whatever the height y is. Huh. Do we have a way that could represent the height of this point? Yes, we do. That sneaky little guy right there is our constraint. It's going to help us out. So we know that y has to be 16 minus x squared. And all right, that's already isolated. What say you? We make ourselves a little substitution, just like we did last time. So then that would make our area function. It's only going to have variable x in it. So I'm going to say it's a of x, again, would be 2x, because that was our base, times 16 minus x squared. That's our height. And now we're going to finish off the same way we did last time. We're going to need to derive, since we're trying to find a max or a min. Other problems will find minimum. We're going to set it equal to 0 to look for tangent lines. If it was possible, you'd also look for where that's undefined, but that's not going to be possible here because you're going to have a polynomial. Just like last time, again, when you derive, you can product rule this, but who wants to do that? I don't, especially since we're going to have to solve something with it. I would much prefer to derive this, having simplified it out. So I've told you a lot in this class that you don't always need to simplify. Don't simplify unless you need to. These are cases where you would want to, because it's just going to make your life easier. Okay, there's our derivative. Since we're looking for a max or a min, I would set it equal to 0. 32 minus 6x squared equals 0. Or I would also check where it's undefined, like I said earlier, but I can't because it's a polynomial, so it's defined everywhere. Let's solve for x. So 32 equals 6 squared. Divide both sides by 6. X squared equals, and each of those is divisible by 2, so it would be, you could either say 32 over 6 or 16 over 3. I guess you could turn it into a decimal, but fractions might be convenient here because we're going to need to take that square root, right? So then we'd say x equals, and I guess if you were just truly doing it algebraically, it'd be square root 16 over 3. It should be plus or minus 4 over root 3. I'm not necessarily going to clean that up anymore. You certainly could. I'm not going to. And it kind of makes sense that we have a plus or minus because, hey, here's our positive one, and here's our negative one. Whoops, that's supposed to be a negative. Even though, well, I'll come back to that thought in a second. Okay, so like last time, we got to ask ourselves the question, did you find everything? It's really easy to stop. Once you're like, oh, I got an answer. Yeah, you answered the work you were working on, but did you come up with the largest area the rectangle can have and its dimensions? We came up with one dimension, so let's go ahead and find the other. We didn't even come up with one dimension, did we? We found this. We found an x, but our base was 2 x's. So one base would be 2 x's, which would be double for root 3, which I guess would be 8 over root 3. Okay, so there's our base. That's one of our dimensions. We would also need the height, which thankfully we have y equals 16 minus x squared to help us out with that one. So our height would be 16 minus, and here again, this is why I kind of left it as a fraction, because it's going to be really easy to square this guy, and instead of having a decimal where it could get cluttered in your calculator. So this would be 16 minus, oops, that's a mistake. That's a mistake. Sorry, it's not a mistake on the screen. It's a mistake in my notebook. I am relatively certain here. I have 8 over root 3 in my notebook, but that's not length x, that's length L. So let's go with this one. So that would be 16 over 3, since it gets squared, which would be 32 thirds. Okay, so there's our height. And then for our area, that's where we just got to multiply them together. Which, at this point, definitely make your calculator do it. Make sure you round to 3 decimals, 2, 6, and then 7, because the next one would round down. Did we have context? We did not, so you can stop it right there. You do not have to write units squared or anything. If you do have context, answer in context. If you don't worry about it. Okay, I know it takes like a lot of work to solve one problem, but it's relatively formulaic, right? We have to identify a couple things. We have to identify the quantity we're trying to optimize, maximize or minimize. What's the constraint? What's going to help us get that down to one variable? And then from there, it's a pretty canned response. Verify, find the max or min by taking a derivative, set equal to 0, or figure out where it's undefined, and make sure you answer everything. So how's that? kind of for our procedure here. And you know what? We skipped step 4 on this problem, so that's my bad. So let's go ahead and take a second to do that. What's our first derivative? We could just derive that again, do the second derivative test again. Okay, so a double prime of x would be 32 would go away, negative 12x. Okay, now where's our critical point? We used positive 4 root 3, which would mean a double prime 4 root 3 would be negative. Therefore, by the second derivative test, that has to be a maximum. I really should have chose a different color for this. I'm sorry. So x equals 4 over root 3 is a local max. I'm sorry I skipped that. Okay, that's everything. Good stuff today, guys. See you tomorrow.